Yes. So next week y'all get to play with the toys with this little Geiger counter meter. This one's nice because it actually has a click associated with it. You can hear it click. We're going to be talking about the concepts of time, distance, and shielding, and how we protect ourselves from radioactive materials, and how easy it is to detect them. So we'll start today with just talking about what's going on with nuclear chemistry and nuclear transformations. So you're going to be frustrated a little bit by this lecture because we tell you to balance your chemical equations, okay, same number and types of elements on both sides of the arrow, and we're breaking that today. so things on the periodic table start hopping around, and your products and reactants don't match. But there are some things that balance, and so we'll talk about that. With the neutrons balance, the protons balance, but the chemical symbols change. Okay, so we need to go back to freshman chemistry, Chem 1, actually, the very beginning, and talk about the terminology for our atomic symbols. We rarely include all of this because we don't really do that much with isotopes. Okay, but in nuclear chemistry, we really have to focus on the isotopes because some isotopes are radioactive, some are not. Think of carbon-14, right? It's radioactive form of carbon. Carbon-12 is the most abundant. And so here we have this, and so we have the mass number, which is in blue here. So that's so focus on the terms, right? The mass number, that's telling you the mass of the nucleus, really to the ones place, right? And it's the atomic number. Think of the atomic number and the element are tied to each other. So the atomic number is the number of protons. Okay, the mass number is protons plus neutrons. Okay, so this is total, and it's 6 protons. So if you do the subtraction, then you end up with 6 neutrons. So that's what makes up the carbon-12 nucleus. Pretty straightforward. You guys knew that. But the thing that's tied strongly are these two things. So a lot of times we can leave the 6 off because C and 6 go together. If it's 6 protons, it's carbon. If it's carbon, it's 6 protons. Anytime, always. So that's what identifies it as carbon. But the 12 can change. The 12 tells you what isotope you're dealing with. So if we're talking about isotopes of carbon, we got carbon-12, carbon-13, carbon-14, and those are our different isotopes. They're still carbon because they have 6 protons. Okay. And morning. So the mass number identifies the isotope. So the isotopes have the same atomic number but different mass numbers. Those are, what we mean by isotopes. There are 3 abundant isotopes of carbon. Okay, so here we are, carbon. We have carbon-12 and 13. Those are the naturally occurring ones. You see 98.93% carbon-12, 1.07% carbon-13. That pretty much counts for everything. So this minuscule amount of carbon-14, we'll talk about where that comes from in a future lecture. Okay. So the naturally abundant stable carbon is all accounted for by 12 and 13. And notice when it says stable on here, that means they're not radioactive. So the radioactive isotopes actually way more abundant than at least in terms of the identified species. We've identified way more radioactive isotopes than you would expect, So yeah, there is a carbon-11, a carbon-10, a carbon-9, but they don't last very long at all. It's carbon-14. This is the half-life. So in 5,700 years, half of it would disappear. So it sticks around for quite a while. Okay, but like carbon-15, 2.5 seconds or 2.449 seconds. So if you have any, it's gone in 2 seconds. It's cut in half. So a good rule of thumb is 10 half-lives. So 20 seconds, it's all gone. Yeah. So this is the chart of the nuclides. You can go here to this Berkeley National Laboratory or Brookhaven National Laboratory and look at the chart of isotopes. And this is just a really cool picture out of a cloud chamber. I've tried to make cloud chambers unsuccessfully, but this is what they show. So what they do is they have a supersaturated vapor, typically of alcohol. So you have some like felt soaked in alcohol on a cool surface. And so it's almost like a cool morning where fog hasn't quite formed yet, but it's ready to form. And a charged particle goes through there and creates a little ion trail, and that causes water droplets to form. Or this case, it causes ethanol droplets to form. So you've got a clear atmosphere ready for that ethanol to bump into each other and form micro droplets, and a charged particle goes through, ionizes one or two of those ethanol molecules, and then they collect all the other ethanol molecules to it. Because the electric charge, Coulombic charge, has a longer distance than, say, hydrogen bonds. So they don't really quite find each other, but if there's an electric charge, then they get attracted and they find each other. So they form these little tracks. So this is probably a uranium ore or something like that, and it's spitting out alpha particles and beta particles. And there's gamma rays too, but the gamma rays don't typically show up in a cloud chamber. So the naturally radioactive elements are shown in red. And this americium down here, element number 95, that is in our smoke detector. So this is a smoke detector. And I've taken the cover. This is the actual americium 241 in that there's a little tablet in there. And it's highly radioactive, okay? And they have a cover that goes over that measures the signal from that americium. So it's feeling those alpha particles and charging up. And so this device is monitoring the charge on that little cover. Okay. Now, alpha particles are so easy to block by smoke, or paper, or even more than like a quarter inch of air. And so you've got this little device, and if the smoke gets between this source and the cover that's sort of measuring the signal from that source, then it knows there's smoke in the room. So it's super sensitive. And that shows you how easy alpha particles are to block, because just smoky molecules will get in there and change the signal and block the alpha particle beam. We'll measure how radioactive it is in a minute. So that's americium down here, some so-called man-made element. Everything beyond uranium we would call man-made, even though we've found examples of natural nuclear reactors in certain mountain formations. And so some of these transuranic elements, so these are beyond uranium, so transuranic elements, they're very, very rare. Only in certain places on Earth have we had sort of spontaneous nuclear reactions where we can form some of these transuranic elements. Okay. This technetium 99M is one that we use every day in hospitals all over the world for nuclear stress tests. So they'll inject this into you, and it basically goes in your bloodstream, and your bloodstream is now radioactive. And so then they can image the blood flow around your heart. And so they have like a collimated beam that moves around and scans your heart, and they can see how bright your carotid arteries are. Not carotid, pulmonary arteries. So the arteries that feed the muscles in your heart will glow because they're emitting light, and that light is able to penetrate through your body, and they can detect it with these detectors. And so that's what we see with technetium 99. And it was one of the last elements discovered because every time they would isolate it, it would decay away. Okay, and so you think you got your element, I'll get around to analyzing that tomorrow. You come in tomorrow and it's missing. What happened to it? Who stole my element? And so nothing happened to it. It decayed away. And notice that all of these elements will eventually. We'll talk about what happens. They decay away, and eventually they end up being either bismuth or lead. And so lead is about the largest non-radioactive naturally occurring element. So all of these, we can push them up beyond lead, but then they're unstable and they break down and come back towards lead. So they're just too big. There's too many protons and neutrons in the nucleus for it to be stable. So it just starts breaking apart. So how do these break apart? These are the different transitions. And so this is the meat of today's lecture, is these different transitions. We call this alpha emission, or also we call this alpha decay. So I use those interchangeably, probably use alpha decay more often. So it's this uranium element, 238, with 92 protons. is decaying away, like it's transforming. And look, there's no uranium on the right side of the arrow. So what happened? Well, this alpha particle came out of the nucleus. And an alpha particle is defined as this. It's four particles in the nucleus, and 2 of them are protons. So 2 of them are neutrons. Well, we know of an element that is 2 protons. That's helium. So this alpha particle is also a helium nucleus. It's coming out of the nucleus. It's coming really extremely fast. It travels through air, grabs 2 electrons, and becomes helium. So this is where all the naturally occurring helium in the Earth has come from. So if we took 2 protons away from uranium, this is the balancing part, right? 2 plus X equals 92. And so we just got to figure out what the other element is. So once we determine that 90 balances it out, then we go to the periodic table and we find element 90, okay, which is over here on this side. So it's element TH, thorium. So that's how we do it. We have the alpha particle leaves the nucleus. So we know the 92 is now down to 90. And then we go look at the periodic table. And if you think about it, anytime we lose an alpha particle, we just move left 2 spots. So alpha decay moves the element identity left 2 spots because it's taken away 2 protons. So from thorium, if that spits out an alpha particle, we're at 88. So then we got to go on a search for 88. It's over there. You see radium? Okay, and then if radium spits out an alpha particle, it goes left 2 places. So where does it go next? 86, radon gas. So that's where radon gas comes from. Uranium deposits in the earth, spits out an alpha particle, becomes thorium, spits out another one, becomes radium, spits out another one, becomes radon gas. So that's called the daughter elements of uranium. Okay, so let's balance the other things too. The alpha particle took out four total nucleons. Nucleons are both neutrons or protons, just non-specific. So the term for any particle in the nucleus is a nucleon. So it took away 4 nucleons and from the 238, so we have to have 234 here. So that's the particular isotope of thorium that's produced by alpha decay of uranium. And so these are the kinds of questions I'll ask you on the homework and on the test. I say you've got uranium-238 and it spits out an alpha particle. What's the isotope left? So not only do you need to know that it's thorium, you need to subtract 4 from 238 to get to 234. And then you know it's thorium-234. And then I put in here, a lot of the books will leave this out, but this plus gamma, the energies of the particles and everything, they don't all match exactly without this gamma. So this is light that's emitted. So every reaction produces a bit of gamma rays too, to balance out the energies. So that's the alpha emission. Maybe you've heard of beta emission. So beta particles. This is a little weird one, okay? A beta particle is also a high energy electron. So beta minus 1, 0 is equal to an electron. So we've seen electrons before, but we never put these other numbers on there. And so it's like it's got a -1 down here in terms of the protons, which kind of helps you understand how it balances with the rest of the reaction. Okay, it doesn't mentally make sense that it's a -1 proton, right? Because it's not an antiproton. There is such a thing as an antiproton. It's just in reactions, when you have beta emission, in balancing the reactions, it's you have to take away a proton from whatever side the beta particle is on. So let's think about that. So 54 xenon minus 1 equals 53. So 53 for beta emission from iodine produces a beta particle. So you know that. If I say it's beta decay or beta emission, you can write out of iodine 131. You know this. You draw the arrow. You draw your beta particle. Make sense? Now I've got to get both sides to match. So see, I'm telling you the procedure. You've got the element. It's beta decay. You know the element. You know the beta particle. So you got to memorize the beta particle, the alpha particle, and all of that. Now you got to make it balance. So I've got a -1 on the right, and I got a 53 on the left. So 54 minus 1 is 53. So now I know I'm dealing with element 54. Then I go to the periodic table and I find it. Xenon. So now I put the xenon there. And then I know that the beta particle doesn't take any particles away from the nucleus or add any particles to the nucleus. And so it's still 131. So this is xenon 131 that's produced by beta decay of iodine 131. So there's a lot of balancing, but it's simple numbers. It's all just addition and subtraction. But if you don't know what a beta particle is, you can't do it. Okay. And then gamma is in there to balance. Okay, then positron emission. This is kind of weird. You've heard of positron emission tomography, PET scans? You heard of PET scans? Yeah, that's what that is. Positron emission tomography. Tomography is just the computer coming up with the 3D structures. So, CAT scans are computer-aided tomography. So it's X-rays, but the computer is coming up with the 3D structures that it's analyzing. So the tomography part is just the 3D structure imaging. So the front part is what the technology is, positron emission. What is a positron? Have you ever heard of that? Yeah, do you know what it is?
I don't know what it is. I've heard the word.
Yeah, it's antimatter. What? Have you ever heard of antimatter?
Yeah, sounds fake.
In the movies, yeah, it sounds totally fake, right? Right. But it's not fake. We use it in our hospitals. Like we're using antimatter to scan people's brains. It's so weird, yeah. I mean, it really does sound like science fiction. But we have some elements like boron or like carbon-11. If we can form carbon-11 in a nuclear reactor, then we can isolate it. And we can make a sugar molecule out of it, right? It's carbon. So we put carbon-11 in sugar. And then we inject that into people. And wherever the sugar goes, this carbon-11 goes. What is going to use up a lot of sugar in your body if you're sick with cancer? Yeah, they're voracious eaters because they're dividing and dividing and dividing. So they got to build their cellular structures. So their metabolism is out of control. And so if you're sending something into the body that's sugar based, it's going to go right into the cellular structures of that cancer, and the cancer is going to glow like crazy. Okay. Now it's not going to glow until it spits out this positron. So carbon 11 has 6 protons and only 11 neutrons, and that's an unstable nucleus because it doesn't have enough neutrons to stabilize all of those protons. And so one of the possible ways to remedy that unstable situation is for one of those protons to sort of spit out its positive charge and become a neutron. Isn't that weird? So how does it get rid of its positive charge? It spits out an anti-electron from the nucleus. So this is a positive electron. That's why we call it antimatter. It's the antimatter of an electron. I've never really heard it called decay, but technically I guess it is. Because any element that's just by itself and all of a sudden spits something out, we would call that a decay process, yeah. And so this positive electron, it has an effect on that reaction of a proton. So it's like a proton left the boron, but it really didn't leave, it just became a neutron. But anyway, to balance things out, the positron counts as +1, the boron count here has 5, and so those add up to 6. And so you see the proton row matches. And then again, you got to memorize what a positron is so that you know it's a +1 and a 0 on top. So the nucleons aren't changed. The carbon still has 11 nucleons when it becomes a boron 11, and just out comes this positron. Now, how do we image this? Because the positrons in this world of mostly matter, very little antimatter, you have this annihilation reaction. So let me go down here. Here's the annihilation reaction. So you've got a regular old electron. Okay, this is the one we're used to, an electron, interacting with a positron and giving 2 gammas. So that's called annihilation. And the mass disappears. So we have matter and antimatter colliding, and out comes light. So the matter is completely converted into light. So that is really cool. And that happens wherever the positron comes. So wherever that sugar was in that cancer molecule, the positron comes out, it finds an electron, because think of all the electrons and all the chemicals in the body. I mean, it's not going to go very far at all. As soon as it comes out of that nucleus, it's going to find an electron. They're going to hit each other, and then 2 gamma rays are going to come out. And we'll talk in the future lecture about how that helps us image very, high definition images. But this is the nuclear transformation part, so that we actually get to play around with antimatter when we're doing nuclear chemistry. Yeah, it's really crazy. Now, from the freshman year forward, okay, back in the day, in the freshman course, when students are learning about the electrons sort of orbiting the nuclei, we sort of think of a planetary model. It's not accurate, but that's the way the brain works at that point. You're like, okay, I haven't really learned about quantum mechanics and wave dynamics, so I just think of this electron spinning around the nucleus. Okay, what keeps it out of the nucleus, right? Why doesn't it get sucked in? They're both opposite charges. Well, they do get sucked in. We told you at the time they don't. Okay, because it's pretty rare. It's pretty rare, granted. That's what I said. You're going to be upset today. You're going to learn about anti-electrons. You're going to learn that the nucleus can grab an electron. Now, only for the really heavy elements that have lots and lots of protons. But that 1s electron is trying to stay out of the nucleus, and it's got a really high energy wave function and so on. But it can happen where it gets sucked in. Now, what happens when I have a proton and electron that get together? They charges cancel, and the proton becomes a neutron. So we have this reaction. We have a proton. Okay, we'll do 1, 1, plus an electron. Okay, -1, 0 gives a neutron. 0, 1. So this reaction is that proton plus an electron gives a neutron. For positron emission, you could have let's see, what do we have? There we have sort of the opposite. We have 1, 1 giving a neutron, 0, 1, plus a positron, 1, 0. So the proton can spit out a positron and leave a neutron. A proton can capture an electron. That's what's going on here with electron capture, and become a neutron. So protons and neutrons can swap places using positrons and electrons. So let's balance this. So if we have electron capture, we've got this uranium-92, huge amount of protons, 92 protons in the nucleus. And it's not impossible for one of those 1s electrons to get sucked into the nucleus. And so it's got a -1 here. So all you got to do is know what an electron is. Same as a beta particle, but we're talking about this electron capture, so we'll use the E for electron. So this -1 down here with the 92 produces a 91. So then we go to the periodic table, and we find element 91. We see that's protactinium, Pa. And then the electron doesn't change the mass number, so it's still 234. So once you know your particles, this is all simple math. But just conceptually, it's weird, right, to see the elements hop around on the periodic table. Would you agree? Yeah. Okay, so then we have fission and fusion reactions. So this is a spontaneous fission reaction. This is what they were searching for during World War II, like prior and during World War II. They were trying to find an element that would spontaneously break apart and produce more than one neutron. So we'll talk about nuclear power in a future lecture, where we can use these 2 neutrons to cause stimulated fission. So spontaneous fission starts it off, and then the neutrons allow us to stimulate fission in other elements. But let's look at this. So 92, all you have to do for this is to have two numbers that add up to 92. Okay, so we got 38 and 54. So 8 and 4 is 12, carry the 1, 5 and 4 is 9. So we got 92 protons distributed over 2 elements. And it can be a wide range of elements. I mean, it could be 55 and 37. So this could produce cesium, and what's 37? Rubidium? Yeah. So it could just as well produce those two elements. So any two numbers of protons that add up to 92, we're good. Now there's going to be some that are more probable than others, but fission reactions generate a lot of different elements, and those would be the daughter elements. And so then you've got to take, this is where it kind of gets tricky. So the xenon at 54, oh, and also you got to know how many neutrons it produces. So in this particular nucleus, it produces 2 neutrons. And so that's going to change the mass numbers of these guys. And so you just got to find somewhat stable isotopes of xenon and strontium. So we look at xenon up here, 54. Look at its mass number, or its mass, 131.3. So it's going to be close to 131. And so that's why we picked the 131 on here. So this would be a very stable version of xenon, because that's very close to its molar mass. You see that? And so then the other one, strontium, is 101. So look at strontium. What is its? Well, it's got 38 protons. What's its mass? I can't see it from here. 87. So this one, I have to come up with 101 because I've got 131 here, I've got 2 here, and I've got to add up to 234. So this one, all that's left is this 101 for strontium, and that's not equal. Let me do this. Not equal to, what'd you say the mass was? Say again. 87. Okay. Therefore, very radioactive. So fission produces a lot of daughter elements that are very radioactive because of the way the mass numbers work out. And so if your mass number is way different than the molar mass of that element, like look at strontium again. It was, I never can remember, tell me. So 87 or 88, that is its stable mass number, 88 or 87, It's going to be a mixture of those anyway in nature, right? And this fission reaction produced a 101. So that's way different than 88. So it's going to be an unstable nucleus. And an unstable nucleus is going to be radioactive. So the radioactive waste that we have in our nuclear power are all of these elements that are way off from their natural mass. And so they're going to decay rapidly, and then they're going to get closer and closer to their natural mass. And that's what we do with our nuclear waste, is let it decay until it's somewhat stable for storage. Okay, stimulated fission. So if we take one of those neutrons and we hit another nucleus with it, then it can cause fission to happen. Spontaneous fission happens with first order kinetics, and it's just a property of the element. You've got this, rate constant at which it decays, and you're not going to change that rate constant with temperature, pressure, or anything. It's just a function of the nucleus. But if you were to hit that nucleus with a neutron, you can make it unstable, and you can speed up that decay rate really quickly. So the half-life of, say, uranium-238 is in the billions of years. But if we were to hit it with neutrons, then we could get it to decay faster. So that's what we mean by stimulated fission. So here we have a neutron coming in, it's hitting a nucleus of uranium-234, and it's the same reaction above, but now we put in a neutron, and so now we have 3 coming out. The one we put in, and then the 2 more that we got. Okay, so it's kind of like a catalyst. We put in a neutron and we get it back out along with 2 more. This is what we use for making things like nuclear weapons, because this doubling of the neutrons can hit more nuclei. So we put in a neutron and we get more out than we put in. And then those neutrons can hit other nuclei and get more out than they put in. And so we'll see how we use this to generate power or bombs in the future lecture. And then lastly, we have nuclear fusion. So this is the fuel of the future. It's the fuel of our stars. We can make a lithium deuteride salt tablet, and then we can compress it, and we can get it to fuse. And so if you look at this, we've got a deuterium, which is heavy hydrogen. It's a hydrogen with a proton and a neutron. So you see it has two nucleons. And notice how you got 3 and 1, that's the same as 4. And so 2 helium nuclei is also 4. So protons are balanced. 7 and 2 is 9. 8 of those go into the heliums, and it produces a neutron. Okay. And because we have fused 2 nuclei, we have the difference in binding energy between the lithium and the deuterium and the helium. So we add up how much mass is missing, we see there's an enormous amount of energy released. So we'll talk about fusion too. So these are all of the ones that are in our vocabulary for the different decay processes. It's really weird, isn't it? Things are hopping around the periodic table. You start with uranium and you end up with strontium. But it's not bad. You just keep track of the protons and the total number of particles. And how do you balance those out? You got to know what a neutron is. You got to know what a proton is, what an electron is, what a positron is, and an alpha particle. So you got to know those 5 particles, and an electron and a beta particle are the same thing. So once you balance them with those particles, then the rest is pretty easy. So if this is our chart of the nuclides, you know, it's showing all of the it's showing all the isotopes that were ever discovered, and it shows that the neutron must play a role. I mean, the evidence that we get from this chart is that the neutrons seem to play a role in stabilizing the nucleus. You think about how the nucleus is built, right? You've got protons touching each other. They hate each other. They're positively charged. So how are you going to build the nucleus and put all that positive charge in one small space? Okay, it seems that the neutrons play a role because all the stable elements start out and it's 1 to 1. Notice carbon 6 and its mass is 12. So we have 6 protons, 6 neutrons. Look at nitrogen. It's 7 protons, its mass is 14. Oxygen, 8 protons, mass is 16. So we start out at a 1 to 1 ratio of neutrons and protons to make stable nuclei. But eventually we need more neutrons to help out. So then it gets to like 50% more. So the delta stability here goes up, and you see the slope starts to approach 1.5 instead of 1. So and neutrons are along the x-axis. So it's more neutrons to stabilize all those protons. But eventually we get above lead, and it's just too big. And so it starts to break apart. So these are all the elements ever discovered. You can go check that out. So let's zoom in on some of these. So nuclei below this belt have too many neutrons, and they tend to decay by emitting beta particles. So they turn some of those neutrons into protons. Okay. And so this beta particle comes out of the nucleus, and the element moves 1 space to the right. So look at iodine, and you can just learn this based on the periodic table. If iodine emits a beta particle, where did it come from? The particle came from a neutron, and it became a proton. So we gained a proton. You can't gain a proton without moving on the periodic table. So beta decay always moves right 1 space. You can write that down. Beta decay moves right 1 space on the periodic table. If elements are above this line, that means they have too many protons, and they tend to become more stable by positron emission, like the carbon 11 spits out a positron and becomes a boron. So it's moving down towards the belt of stability. Or if they're too heavy and they're above, then they like grab an electron, and again they're trying to get rid of the excess protons, so they could spit out a positron, or they could grab an electron and move towards the belt of stability. And then the alpha particles, if we just have too much in the nucleus. So we got uranium, it's way past lead. We've got too much in the nucleus. It just starts shedding alpha particles, protons and neutrons. So it can move down towards the stable area of lead and below. If you look at the periodic table, everything below lead is not radioactive. except for technetium. I don't know why that element's nucleus is unstable just naturally, but it is. Okay, and so then this just keeps going. So if we have uranium up here, and we spit out an alpha particle, we move down 2 places because it moved down, lost 2 protons. Okay, so we went from 92 to 90, so we're at thorium. Okay, it also moved left several places and lost the neutrons, and so we're now at thorium. And then if thorium emits a beta particle, it's protactinium, and another beta particle, it's back up to uranium, and that can happen. But thorium can also emit an alpha particle, and so the red paths are the alpha decay paths, and the yellow paths are the beta decay paths. And every little stop along the way is either a thorium or a radium or a radon or a polonium or lead. And eventually it gets to lead. These black lead squares are the stable versions of lead. So we can just totally follow all of this. It's called the transuranic series of all of these elements. And we can get into a rock formation and we can see how much of these elements are there, and we can date the rock. So this is how we date a lot of our ancient rocks. So now we can use these particles that come out of the nucleus, we can accelerate them, we can use them for research. And so that's what we've done. And we've made elements in the lab. That's how we made all of these bottom ones. The white ones there that are outlined, those are now official. And we've gone all the way to element 118 by accelerating these particles and things like this Fermi lab in Chicago and the CERN accelerator. So we spin the particles up here in the research facility. This is the injection ring, and we get them going really fast, and then we inject them onto this superconducting area here and get them going really close to the speed of light. We may have 2 beams going in opposite directions through all of these things, and then we steer them into each other. Boom. And for a slight, millisecond or so, we have, some seaborgium or meitnerium or one of these elements. So here's the tunnel. So the particles are going inside this cryogenically cooled accelerator, and they've got electric fields around there. So they just pull those charged particles along with electric fields. So if you want to get them going really fast, you make that arc really big so that your electric fields can be spaced out and get them going really fast. And so that's what's going on there. And then when they hit, you have these little bubble chambers, and the particle tracks go in these bubble chambers. And what are the curlicues? Well, they might put this in a magnetic field, right? So you've got a magnet here north, and behind it a south magnet. And you've got the charge, you got it in a magnetic field. The right-hand rule will tell you which direction it goes. So if it's a positive particle, it goes one direction. If it's a negative particle, it goes the other direction. And how big the arc is how fast it was going. So how fast it turns. Then you can get the mass, you can get the velocity, you can get the charge, and so on. So that's how we do our research. It's a lot like one physicist said, throwing a Swiss watch against the wall and picking through the parts to see how it works. So we really don't know how the nucleus works, but we smash them together and we see the particles that come out, and we've come up with our particle physics models. So let's play around with the Geiger counters and stuff. You're going to have a lab associated with it, but we've got a few minutes to do the show and tell.